Okay, welcome back to the third lecture on entanglement theory for SheQuantum, which is an organization that's supporting women in research and learning of quantum information science. In the last lecture, we talked about density operators for tensor product Hilbert spaces, and we just talked about two parties, Alice and Bob. And then the important thing that we did was we defined what is an entangled state versus a separable state. I have to get the timer going, excuse me. So we defined what is a separable state, what is an entangled state. And then the final thing we talked about was this Schmidt decomposition theorem, how that's an important theorem in quantum information. I guess I forgot to say this point at the end, which is really important, that this gives you a way to decide whether a state is entangled. And I said that to compute the Schmidt decomposition, you'd use the singular value transform, which means that you can figure out the Schmidt decomposition in time polynomial in the local dimensions of the states. So that's something you could execute on your computer in MATLAB, for example. And then a key conclusion is that a pure state is entangled if and only if the Schmidt rank is greater than or equal to 2. Okay. And the other thing we talked about is we talked about the example of the E-bit. Right, that's what we did here and gave you this exercise. Okay, so let's keep going forward. And now let's talk about a new mathematical tool which comes up a lot in quantum information. It's called partial trace. Okay, so we talked about it in the first lecture. What is the trace of a matrix? You can figure out the trace of a matrix just by summing the diagonal elements, but there are other ways you can compute the trace. And in fact, you can use any orthonormal basis to do so. So you take the matrix, you'd sandwich it by each of these elements of the orthonormal basis, and then you'd sum over all of them. And then you get the trace. Partial trace is a generalization of this idea. Okay, so partial trace, it's like if Alice and Bob have a quantum state, if they shared, for example, 2 qubits described by a density operator, maybe you're only interested in knowing what Bob's state is, okay? And so that's where you use the partial trace. So in that case, you trace over Alice's system to figure out what is the density operator for Bob's system. And, maybe Bob does not have access to Alice's system. And so that's all that describes his local system. And then you can use the density operator on his system to predict the outcomes of experiments conducted on his system alone, but don't involve Alice's system. So that's the use of the partial trace. How do you do it? You take these orthonormal vectors and then you compute the tensor product with the identity operator. So you do it for this row vector, you compute the tensor product, you take this column vector, you compute the tensor product, and then you calculate this matrix multiplication, right? So when you do this right here, you get a matrix, this is a matrix, this is a matrix, you multiply, you get a matrix, and then you sum over all of them, okay? Again, for details of the tensor product, if you don't know that, pause the video, do some Googling and Wikipedia lookup. It's also in the book that I wrote with Sumit, Principles of Quantum Communication Theory, a Modern Approach. These are linear operations, so they're somehow more simple mathematically if they're linear operations. And then here's the interpretation that I was talking about, right? So suppose that Alice and Bob possess quantum systems described by the state rho AP. The density matrix for Alice's system you get by doing a partial trace over Bob. And then you can use this density matrix to predict the outcome of any experiment performed in the analysis system alone. Something to realize if you've taken a course on probability theory is that this generalizes the notion of marginalizing a probability distribution, right? So in a previous lecture, we said anything classical we can do in quantum. And so what I'm doing here is I'm taking a joint probability distribution, Pxy, and I'm placing it on the diagonals of a bipartite two-party density operator. That's what this sum is right here, where these are, these x's are orthonormal vectors, and so these are projections. And same for y. So with the partial trace, if we partial trace over y, we said it's a linear operation. So that means the sum can come out, these scalars can come out. The trace goes inside. It's a partial trace over y, so it acts like a full trace over these. And then some calculation you can do is if you take the trace of a unit vector, the projection formed by a unit vector, that trace is equal to 1. So you just get the number 1, and then this sum over y, you can think of it as happening first, and then there's this sum over x. And so this right here, if you're summing over one variable of a joint probability distribution, that is what is known as marginalizing a joint probability distribution. And so that we can define, that's what we've done here on the bottom. So we'll define Px to be the marginal of this joint probability distribution. Okay, so let's talk about a different concept called purification. And this is something really that's unique to quantum mechanics and quantum information. There's not really any classical analog of this concept. Okay, so what is purification? Suppose we have a density operator rho s for a system S, okay? A purification of rho s is some pure state on a tensor product system R and S, such that when you take the partial trace over this reference system R, you get back the original density operator, okay? So a way to think of this is like, the state of the system S is generally a mixed state, but we can think of that mixedness as being due to entanglement with an inaccessible reference system. Okay, so this psi could describe the state of a reference system in the original system, and it's pure. Okay, and since we don't have access to system R, we can think of it in that way, then you trace over it. And so the rho s is what describes our state. So that's a way to think about it. What is a simple way to construct a purification of any density operator? You can do it according to the standard recipe. So suppose that rho s has a spectral decomposition of this form, right? Px are the eigenvalues. These x's are the ket x's are the eigenvectors. These are the eigenprojections. So what you do is for every index x, you take the square root of the probability, and then you can think that you're flipping this, what's called bra, to a ket, okay? And you give one to the reference, the other to the original system. And then if you take psi and the outer product with its dual vector, and then take the partial trace, you can do a check that after that calculation, you'll get back this operator here, this matrix. Okay, so that's a standard construction. Another important concept is that all purifications of a state, they're related by a unitary acting on the reference system. Okay, so that's an if and only if, right? So if you have two different states, psi and phi, we said they both purify rho s if and only if they're related by a unitary. Okay, so to see one direction of this, suppose that we act with a unitary on the reference system of psi. Okay, then let's look at what we get if we take the partial trace. So we take the partial trace over the reference system. Partial trace is also, it obeys a cyclic property. When we talked about trace, I didn't mention that, but that's something that, a property that trace obeys. So that means with this partial trace, since U is acting only the reference and it's tensor with the identity here, it has a cyclic property, meaning that we can bring U dagger from the right over to the left. And then it becomes this. And then since U is a unitary, U dagger U is identity. And so then identity tensor identity is just the identity. That's like nothing happened. And so then we get back to this statement here. And we're starting with psi, the assumption that psi itself is a purification. Okay. To prove the other direction, you can use the Schmidt decomposition. Okay. So what is the important use and interpretation of purification? It does get used a lot. As we said, it does not exist in classical theory. So what it's saying, and it's related to entanglement, a pure state is like a definite state. It's like we know for sure that the system is described by this the state. You know, it's definitely that possibility. It's not in a mixture of possibilities. So the situation here is such that the joint state is definite. The system, the state of the joint system is definite, but the state of the individual system is mixed, right? So generally this PX can be a full probability distribution with a bunch of different numbers there. That's really a mixed state. So that simply doesn't happen in classical theory, right? Like you don't have a definite state of two systems such that the individual systems are indefinite. It just doesn't happen. So it's very different from the classical theory. Okay. And then this is the interpretation we were talking about previously. Noise or mixedness at a quantum state is due to entanglement with the reference system. There's also an interpretation in the context of cryptography, right? So in quantum cryptography, what we do is, you're trying to get a secret key from a quantum state, rho AB. And what we assume is that the system A is definitely in Alice's laboratory. The system B is definitely in Bob's laboratory. And we assume that those are secured labs. Okay. But then what we do is we just, because we're sort of paranoid or scared about eavesdroppers, we just assume that an eavesdropper has access to the full purification, to the purifying system of this density operator, okay? And really, the interpretation is we're giving Eve a lot of power in that scenario. We're saying Eve actually has access to every other system in the universe that Alice and Bob do not have access to. So it's a very strong assumption, and it's part of the reason that quantum cryptography is viewed as, in principle, totally secure, right? But it's difficult to actually build these systems in practice. Okay, why don't we stop for there? I think it's a good stopping point, and then the next lecture we'll pick up on quantum channels.